All right. Well, I've been with TDEngine. We are an open source time series database. I've been with TDEngine for the past 2 years. TDEngine was started first by Jeff Tao in 2017. This is his third startup. And in 2019, I believe he open sourced it. The company is based out of Beijing. All of the R&D is in Beijing. And then we entered the North American market about 2 years ago, and we are just starting to get customers. And we have an enterprise solution. Of course, we have the open source solution, which is the core of everything. And then we also have a cloud as a service solution, which is based on AWS and Azure and GCP. So obviously, since you guys know what time series databases are, you know what time series data is. So I won't, oh yeah, I should use this, good idea. But I mean, for the sake of, since we have this slide up, these are all of the use cases where time series database is used. Manufacturing is a big thing now, especially with digital transformation and Industry 4.0. And we'll kind of talk about that a little bit later as well, because there are other kinds of time series databases that have been around for a long time, which are called data historians. And I'll get to that a little bit later as well. So what are the uses of time series data? One of the biggest ones is, of course, forecasting, and this is especially crucial now with climate change and supply chain shortages and you know, trying to optimize supply chains in manufacturing and processes. And then there's also another big thing is anomaly detection, which is also kind of closely tied with preventive maintenance, and this is especially useful in manufacturing, wherever you have field service engineers that are going out and repairing things and they're deploying instruments and equipment. So these are all the places where time series data is very useful, and analysis of time series data is very useful. And then, of course, all of these things put together basically provides insights into business operations, right? So one of the things is that time series data does have certain characteristics. Some of these things are pretty obvious. Obviously, the data is all time-stamped, but I think the key thing, in my opinion, besides all of these things, is that the data itself is typically a function of time. And this comes into play, and a good way of thinking about it is, for example, time series data may have seasonality. And a good way of thinking about that is, let's take, say, retail data, for example, right? Retail store sales data. Obviously, during times of the year like Christmas, there's a lot more sales going on, and there's seasonality in that data. So you'll have, like, you know, when Amazon has their Prime sale and other retailers try to match the discounts, there's a huge surge in sales. Or obviously, weather data is seasonal, pollution data is seasonal. So that's what I mean by the data itself is kind of a function of time. But these other things are important as well. So for example, in time series data, the fact that transactions are not required means you can optimize your database to be very write heavy, right? And data is not updated very often, so transactions are not really required. That's another important thing. There's also this idea of retaining data for a certain period of time, because very often data that is more than a certain number of years or months or whatever it may be, depending on the use case, is not very useful. And so you can either archive it, or in some cases you can even delete it. And so it's helpful to have a retention policy built into the database that says, as your data ages, you can get rid of it in some way or the other. The other thing is that, the other important thing is that usually there's real-time data computing going on the data. So for example, if you have a pump that's, say, giving you data at 1,000 hertz, getting all that data may not be very useful, but the aggregate data might be. So you can do, for example, fast Fourier transforms in the data and then store the results of that in the database. Or you can do some other kinds of aggregation and then store that in the database rather than storing all of the raw data. And obviously, queries are always using some kind of time-space range when you're doing queries. Like there's almost never any query where time is not a dimension, right? And so the reason I'm mentioning all of these things is that a good time series database will kind of exploit these characteristics to optimize the database for time series. And the key is that you're really storing time series data. It's usually stored in a columnar way, and typically you're not storing any other kind of data. It's always just time series data because that's what it's optimized for. So these are some of the other time series databases out there. InfluxDB is basically the oldest one, I would say. Actually, OpenTSDB is old as well, but InfluxDB is like the most established player in the market. They're based out of San Francisco. They've been around for probably 15 years at this point. Timescale, they're open source as well, and they just moved to version 3.0, which is based on Apache. And then TimescaleDB is based on Postgres. There's us, TDEngine. QuestDB is another time series database that's based out of the UK. Everybody knows Prometheus. Victoria Metrics is very well known. RRD tool, if you guys have been around in the industry for a while, you're laughing because of the, yeah. So anyway, if you've been in the industry for a while and you've done any sort of network monitoring, then you know RRD tool, right? So, so why do we need a time series database when obviously other databases, including TiDB, can handle time series data? The key is that these databases are really highly optimized for ingesting data at a very high frequency. They try to lower the query latency as well. The queries themselves are optimized. And then, of course, storage costs. So most time series databases will have very high compression. So does TDEngine. And we have situations where we've compressed by more than 60-70%, and that really does reduce storage costs significantly. There have been customers that used to have terabytes of data in a single day with other databases. These were not always time series databases, but then when they moved to TDEngine, they were able to say lower down to close to 100 gigs a day from a terabyte, right? Other features of time series databases, data lifecycle management, that's very important because as I mentioned before, this whole idea of data retention, as the data ages, it's removed from the database. So that's pretty important. There's also other things you can do, like you can move older data to slower storage, for example, not just to reduce costs, but just to make things more efficient. The other thing is roll-up, which is essentially aggregation. So you can have data that's streaming in, and then you're aggregating it on the fly. All right. So you might be doing time-weighted averages. You might be doing other functions as the data is coming in, and then you store that data in an aggregated way, so that any clients like analytics software that's querying these databases is querying on the aggregated data. And then they don't have to do the aggregation themselves. The data is already there. So that reduces the experience as well for business analysts and people that the people in the business side of things that are interested in querying big data. Yeah.
So you mentioned RD tool. So this concept of roll-up. So RD tool has its own.
Yeah. Yeah.
Is that a must or is that?
No. So in our database or in most time series database, it's not mandatory to do the roll-up. So we don't automatically do the roll-up, but you can configure the tables or configure the streams rather to do the roll-up, and then store the data in a secondary table. And you can do pretty much any kind of aggregation you want in the stream. Yeah. You don't have to. No. Yeah, it's just a question of what your application is going to do with the data later on. And so you have a lot of flexibility built in to decide what kind of roll-up you want to do, basically. Yeah.
What about filtering aging data out? Is that like a TTL you set at the table?
Yeah, exactly. You can say, like, for example, you can set it to be 10 years, right? And then if today is the 10th year for a particular series of data, it just disappears. Or you can even, like I said, you can actually also configure it to move it to lower cost storage. So that's another feature of Yeah.
And if it does that, can you query against sort of that hot data and cold data together?
Oh yeah. So actually, that's a good point. In most time series databases, you will not know the difference between when you're querying anyway, between how old some data is and so on. And they're really fast. Like you can do, aggregation on years and years worth of data in seconds, essentially. Another good thing is interpolation. So this is a function that's built into the database, because one of the things that happens with the time series data is, especially if it's coming in at a very high frequency, you can actually afford to skip some data points. Like if the device drops out for 10 seconds, no one's going to notice really, because you're usually interested in the aggregate data, not the data that's coming in every millisecond. But when you're doing some queries and you need interpolation, like you need to fill in that data, then there are various mechanisms to fill in that data, and that's provided in most time series databases as well. So continuous query, because the data is streaming in and you want to be able to do continuous queries on it as well. So in the time series database, you'll typically have some mechanism where you can do continuous queries on different kinds of windows, sliding windows, session windows, state windows. And again, this is useful when you have dashboards that business people are looking at or operators are looking at, and you don't want them to have to query from scratch. They're just querying again on aggregations of the data and more recent data, not old data. So having continuous queries is very useful. Time series databases are becoming popular. If you go to dbengines.com, you can see all the stats for it. And one of the reasons is that there's just a huge increase in the number of devices, essentially. Not just devices that we own, but also devices that are querying equipment and IoT and, so I mean, everything from medical devices like glucose meters. There's even a company in the Bay Area, I think, that has these I don't know what they're called, massage things, and they send data to their central servers. Yeah, I mean, all kinds of data. So there's just an exponential increase in data, basically. IT infrastructure is obviously expanding, and so on and so forth, right? Lots of devices sending lots of data to the cloud. And these devices are sending very small amounts of discrete data, but there are just billions of devices, and that's what leads to so much data coming in. Criteria for selecting a time series database. This is obviously a marketing slide, but I'll go through it anyway. Open source is always good because you can actually see what's going on with the code. And so TDEngine is open source. InfluxDB is open source. Timescale is open source as well. But with TDEngine, you actually get, I would say, most of the features, including all the distribution and scalability and the clustering, high availability. That's all available in the open source version. It is cloud native, so you can deploy on containers. We have Helm charts as well. We do have we have an observability solution built in using Grafana. So we do have integration with Grafana. And another really important thing, in my opinion, is having a standard query language. So Influx, for the longest time, for example, had their own query language. We just support standard SQL. And we do have some additional functions that we've written that are appended to the SQL, but those are you're still doing standard SQL, and just the function name changes depending on what you're doing. What else? Scalability, performance, everybody has that. We do have some specific features, I would say, some novel concepts in our database. So we do have this idea that there should only be one table per device. This is not typically how you would do database design in a relational schema, for example, but this is what we do in TDEngine. And then on top of that, we have this idea of a super table. And what a super table does is it basically, based on the one table per device concept, a super table essentially acts as a container or as an abstraction really for a type of device. So let's say that you have a smart meter from PG&E, and most smart meters will report voltage and current and maybe a few other things. So what you would do in our case is you would create a super table that represents the abstraction or the object of a smart meter. And then it has metrics that it's monitoring, so voltage, current, whatever else. And then it'll have some tags. So it'll have the location, perhaps, the device ID, maybe some other tags that are useful to PG&E, right? And then the tables under it. And the cool thing about it is that you don't have to care about the names of the devices or anything like that. You're just querying on what we call tags. For example, the device ID, and you would just query the super table. So you query one table, you don't query the underlying subtables. So for example, with the meters analogy or the example, you could have, I don't know, 10 million meters from PG&E, and you would still query the super table, and now you can do aggregations across the tags. So tags are essentially attributes of the data. So for example, the location of the meter. So it could be a city, it could be a district, it could be a state, right? It could be Southern California, Northern California. Now you can do all these aggregations by just querying the super table and saying, I want to filter this on this tag, essentially. So it's kind of a little bit tricky to understand, but if you go to our website, you can see all the examples of how the super tables are done and the subtables are done. And it's kind of an interesting concept. It's not relational, but just like relational databases, we do support joins and so on, right? So it's kind of a mix, I would say. But there's no normalization. Like in a relational database, you would do like, the 3NF or 4NF, and we don't do any of that. So there's no third normal form, fourth normal form. It's just data. And it's all stored as columns. It's a columnar database, essentially. So, so this is kind of something about TDEngine. We do have connectors for Telegraph and Kafka and OPC, which is the industrial protocols, MQTT. We do have integration with Grafana as well. We have APIs in most of the languages. We've mentioned Python over here, but there's also Java, C, C++, C#, Go, Node, and then of course REST APIs. And then we have a really good command line like a shell. I use a shell all the time. I don't like our web-based management tool, but it's very good, okay? It's very good web-based management. If you like web-based management tools, it's excellent. But you can do everything in the command line interface as well if you're into that. The web-based management tool is not available in the open source. It's in the enterprise, but it's available. This is the architecture. And again, this was kind of built from the ground up for distributed computing. So this is the logical architecture. The D nodes are sort of based on they reside on physical nodes. And then each D node is split into, a D node is sort of this, like the basic unit that we have. It's the Taos daemon, the Taos server is running on a D node. And then within the D node, you have what are called V nodes. These are virtual nodes where this is the basic unit where the time series data is actually stored. And then it does all the sharding and partitioning. And then we also have query nodes, so that's Q1. I should use this. But anyway, I guess I'm just not very used to this. But anyway, the Q nodes are the query nodes, and those are self-contained computing units. And they are not tied down to a particular database. So Q nodes can be launched by the cluster at will when more computing power is needed. So there's a separation between storage and computing, essentially, right? And then we also have the M nodes, which are the meta nodes. And what the meta nodes are doing is they are keeping track of the cluster, making sure that D nodes are up, V nodes are up. And then it also has data on the structure of the schema. So it knows tables, subtables, supertables, and keeps track of the tags and everything. And then yeah, essentially, you would then create clusters of TDEngine instances using this architecture, basically. So depending on what you're using, for example, if you're using a virtual machine, you could have 3 virtual machines, each with 1 D node, and then TDEngine will figure out all the clustering. The cool thing is that there's no administration really required. It's horizontally scalable, and you don't have to worry about how the logical architecture interacts with the physical architecture, essentially. Questions?
Does that mean it scales automatically, elastically?
Well, so if you, yeah, so it depends. I mean, there is some correlation, obviously, between the physical architecture and the logical architecture. But for example, if you were using Kubernetes, say, then yes, you could instruct the Kubernetes controller to launch additional D nodes and so on as you needed them. Exactly. Yeah.
I've also noticed that some of the D node doesn't even have a Q node.
Yeah, exactly. So the Q node is launched when it's needed, and then the M nodes will figure out where the Q nodes are, and send the queries accordingly. Yeah.
So always 4 nodes in a D node, or do you have more than that?
Yeah, not so typically you will have the virtual nodes and then the query nodes, and in some cases you'll have what we call streaming nodes, even though they're not shown on here. But basically what the streaming node does is as data is streaming in and it's being ingested, the streaming node will deal with the aggregation and so on. Yeah. Thanks.
When you say there's no administration needed, and when you say, do I have to decide when to, I guess I have to decide when to deploy the machine, but do I have to decide where?
No. So the only thing you have to really worry about is creating the D nodes when you first create the cluster, right? But a lot of the other stuff, like the meta nodes and so on, you don't really have to worry about it so much. Yeah, because when you create a cluster, for example, you'll say, I want to start out with 3 D nodes, for example, and you create the 3 D nodes, and one of them is always the kind of the leader. But if the leader dies, as long as the remaining 2 D nodes are alive, it's still fine. Yeah. And again, you can do all of this from the web management tool or the command line tool. And then in terms of scalability, this kind of talks about how we do the sharding and partitioning. There's a really good blog on our website which really goes into detail about the architecture that was shown on the previous slide, and then how all of the sharding and partitioning happens between the different nodes, in the logical architecture. And there's a very good, very detailed explanation of that. But this, along with the design of the schema, which is the whole idea of the super tables and the subtables, and a single device per, a single table per subtable per device, is what really allows you to scale very easily. So that the logical architecture and then the schema design are kind of very well coupled to allow the scalability.
So am I understanding the time series database doesn't require the administrator to do any design either?
To some extent, yeah, because for example, it won't be a relational schema design. Basically, you will have to design a schema to make sure that, for example, different types of devices are in their own super table, right? So, for example, if you're in a factory floor and you have pumps and you have, say, boilers, you don't want to intermix the boilers and the pumps, because the pump will be in its own super table and the boilers will be in their own super table, because they're looking at different metrics, right? And their tags are going to be different. So you don't really want to mix those, for example. Whereas in relational design, you may have a mix of devices. Yeah, so it's a very different.
Make my decisions based on characteristics that I can perceive.
Yes. Yeah. So here you would have separate tables for boilers and different types of devices. Yeah, so you would tell TDEngine that this is the schema of my super table for my pumps, and a schema for the super table of my boilers, for example, right? Yeah, and there's no normalization, right? So there's no normalization. Yeah, yeah. What else? Yeah, so a little bit more about how the M node works. The metadata for each table is stored in the V node, and then we use a B tree for the metadata store, B plus tree for the metadata storage, and it's really fast. I mean, you won't, like, it's completely transparent to the user where stuff is being stored in a cluster. Essentially, the logical architecture is, I would say, pretty much transparent to the end user that's only concerned with querying the tables or ingesting data into the tables. Even for an administrator, the main concern would be how many nodes you have in a cluster, right? And similarly, for whether you're using VMs or Kubernetes, you're mainly concerned about how many physical nodes and how they map to the logical architecture. In theory, you could have multiple D nodes on the same physical machine if it has enough memory and CPUs, basically. But we are very conservative with using resources. Like on this laptop, it's a pretty good laptop. It's got 4 cores and 16 gigs of RAM, but I can have a table with 10 billion rows and I can do aggregation on it in seconds. And again, it's just because we've really optimized the database. And we don't store anything else, okay? We cannot store images and so on. It's just time series data. So one issue with time series databases, which a lot of people which you will encounter, is high cardinality. And this is the idea that in a particular column, you will have a huge range of values. Like you can have a billion different values, and that becomes really complicated for performance. It slows things down. But that's something that we think we've solved. Again, we can query data in no amount of time, essentially. Some of the other databases do start running into the high cardinality issues. So far in our tests anyway, and you can download our performance benchmarks against the other time series databases. We have 2, one for IoT and one for IT monitoring, and we have both benchmarks, and yeah, we don't have the high cardinality issue, essentially. So yeah, just a little bit more about, and again, all of this is in our blogs on the website, and it's in much more detail. So you can always go to our website and really, and again, our database is open source, so you can also look at the source code for all of this stuff. Ease of use, I kind of talked about this. There's not too much to manage and administer. Data access is really convenient. We have lots of APIs, and we have integration already built in with Google Data Studio, Grafana, and we have a REST API, so you can pretty much use anything. We are in the process of getting an ODBC driver. We do have JDBC drivers already, so we will be able to integrate with Power BI and Tableau and so on. And then, yeah, we do have different kinds of connectors, SQL support, and that's it. So, and thank you. We're open source, so you can download. We have open source downloads for Linux on AMD and ARM as well. So you can always download it, and yeah. And on our website, on our cloud site, cloud.tdengine.com, you can just get a free instance. It's 1 month of free data. I think it's like a single CPU 2-core, or single CPU 4 gigs of RAM. And there are lots of public databases that we've created in our what we call our DB Mart. So you already have time series data you can play around with, essentially. So thanks, everyone.